I did everything right except for it.
Okay. So here's what we have left in this 9 weeks. Okay? Here's what we have left. We have momentum, which is going to take us about 8 days to get through, which puts us at a test again on momentum kind of end of next week. Okay? So there's linear momentum, there's angular momentum, they're pretty straightforward. Okay? Then after that, we've got working energy, and then thermodynamics and gas laws, and that's about it. So we don't have all that many tests left. All right, so let's talk about momentum. Now, momentum itself is a pretty simple thing to calculate. So what do you think determines the momentum of an object? There's two things: mass and velocity. Okay? So momentum is as simple as it possibly gets in terms of the calculation. It's mass times velocity. That's it. Boom. Now, the reason that we use the letter P is basically because we can't let it be M, because then you have M equals MV, and that's just weird. Okay? So the P actually comes from the old Latin term meaning impetus, which is what they used to think how you would describe motion. So what they used to think would happen is that I would throw this tennis ball and I would give it a certain value of impetus, and it would travel until the impetus ran out, and then it would just fall. Okay, so you had like an impetus fuel tank. So if I just put a little bit into it, okay, it doesn't go very far. If I throw it faster, I put more into the tank, so it travels farther before it runs out. So that's where that P comes from, is that old idea of impetus. So here's as simple as momentum problems get. So let's say that I've got a 1 kilogram mass, and it's moving at 2 meters per second. Okay, so I'm going to take 1 kilogram times 2 meters per second. So obviously I get 2. Now what units do I end up in?
No, not newtons.
How about just kilogram meters per second?
Yeah.
Is there a handy little way to write that? Or do we
There is, we'll get to it.
All right, cool.
Okay, so it's kilograms meters per second. Is this newtons?
No.
No, because that would be mass times acceleration. Okay? Now, you'll see why this works through a couple different ideas. But you can also write it as Newton seconds, and here's why this works. Is because if you write it as Newton seconds, well, newtons are kilograms meters per second squared, and then when I multiply that by seconds, the seconds cancel out, I get kilogram meters per second, which is the same thing as that. So you can either write it as kilogram meters per second or Newton seconds. I don't care, pick one, doesn't make any difference, okay? But you have to put something there. Now, do you think this momentum, do you think it's a vector quantity or a scalar quantity? Meet. Vector or scalar? Scalar. Why? It has no direction.
What does it?
I don't know. So, if I take this 1 kilogram mass and I move it this way at 2 meters per second.
Right.
Now, if I move it this way, what's happened to the velocity? Still positive, or is the velocity now negative?
Negative.
So if I take it and move it this way at negative 2 meters per second, now what's my momentum?
Negative. Yes, it is. Yeah. It's not
Yeah.
scalar.
So if I move it in the opposite direction, or take 1 kilogram times a negative 2 meters per second, and I'm going to get negative 2 Newton seconds. So if it's moving in one direction, it has a positive momentum. If it's moving in the opposite direction, it has a negative momentum. So meet. Do you think it's a scalar quantity or a vector quantity?
It's a vector.
It's very much a vector quantity. Because I can even draw it as an arrow. I can go, oh, it's moving this way. This has a certain amount of momentum of 2 Newton seconds. If it's moving this way, it has a value of negative 2 Newton seconds. Okay, so momentum is very much a vector quantity. Okay, So here's the question. Is it possible for two objects of unequal mass to have the same momentum? In other words, could I take this cute little 10-gram mass and make it have the same momentum as a 1 kilogram mass? Ms. Treadway? Yes? What would I have to do? There's two situations where you can answer the question correctly.
Well, if you want to make the smaller mass have the same momentum as the larger mass, then you would just increase the velocity. Right.
Of which one?
Of the smaller mass.
Okay. So one option is that since momentum is mass times velocity, I could have a small mass moving very quickly, or to balance that out, then I'd have the large mass moving
Slowly.
very slowly. Okay? Boom. Now, right now, what's the momentum of the two objects? 0. Right now, do they both have the same momentum? Yeah, or they're both at rest. Okay? But usually when you're talking about momentum, you're talking about a non-zero velocity. Okay? So don't get technical. Well, if they're both at rest, they have the same momentum. Okay? No. And when talking about momentum, I'm talking about a non-zero value. Okay? Ellie, is it ever possible for the 10-gram mass and the 1,000-gram mass to ever have the same inertia? Why not?
Because inertia is related to mass.
How, like a distant cousin?
Well, objects with more mass have more inertia.
Ah, so there's no way that this 10-gram mass can ever have the same inertia as a 1,000 mass. Okay, can't. Because, like Ellie said, the only thing that affects inertia is mass. So this 10-gram mass will always be easier to speed up and slow down than the 1 kilogram mass was. So if they have different masses, they can never have the same inertia, but they can have the same momentum. Okay? So keep that in mind. Now, the test in 8 days is not going to be 40 questions of going, oh, here's the momentum. Here's the mass. What's the velocity? Okay? Or here's the mass. Here's the velocity. What's the momentum?
Can we get a test like that? Since we had a test like the one we just had?
You know what? Here's what worries me. Is that usually the momentum test scores are worse than this test.
What?
Seriously. No, and I'll tell you why. No, and I'll tell you why. And here's the reason. I think that you think, oh, momentum is really, really easy. It's not that tough, and then you don't study for the test. So that's why I think what happens. But since I've started pointing that out, the momentum tests have actually now gone up, and because it's like, oh, don't be a slacker. And so I've seen an upward trend on the momentum test. Now, is it possible, Mara, to change the momentum of an object? No, I can't change the momentum of an object. So I have a tennis ball.
Yes.
Could I change the momentum of the tennis ball?
Yes.
Yes, what would I have to do?
Change the velocity.
By making it,
Bigger. Smaller.
mass stays constant. Yeah, I can make it smaller. Okay. Okay. So changing the mass gets tricky. That's tough to do. Okay. Yeah, I could pour liquid hot lead into it, but that would just be weird. So what do you think is easier to change?
The velocity.
Ah, the velocity. You hit a softball with the bat. Do you change the momentum of the softball?
Yes.
Yes, right? And the harder you hit it, the more the momentum, right with the ages, changes, right? Okay? Now, we're going to do a simple experiment. Kids, I want you to catch the ball.
I really don't know if I can do that. I really don't.
Catch the ball.
Okay, fine, I will catch it, but I don't know if I can do it. I'm just warning
All
you.
you have to do is just throw it back to me.
Oh, I don't know if I can do that either. Let's try this.
Do it tomorrow.
Mara's a lot better.
She is D1 bound.
Okay. All right, here. I'm going to throw this to you. Okay?
Call the coach if you drop
Okay.
it.
Now, did I change the momentum of the ball? Yes. What did I do?
You added velocity.
But I exerted a force.
You're the source.
I exerted a force. Did I make the ball accelerate?
Yes.
Yes. When Maura caught it, did you change the momentum of the ball? Did you exert a force? Yes. Now, throw it back. Okay? Now, if I don't exert a force on the ball,
What if
This
you
is
would
why I'm glad I
have
didn't throw it.
Yeah, what if you
I would have ducked. Okay?
Can you imagine?
Would have ducked.
I don't know. You're not the quickest cat.
I didn't know that happened on accident, so I was like, that was really slow. That was a really slow.
Someone's getting some points taken off his test when he turns it in.
I was joking. You're a quick cat.
I'll go ninja. Don't make
That's
me.
gotta be on the video.
Okay.
Doing that.
All right.
Video.
Now, if I don't exert a force on the ball, does the momentum change? No. So clearly a force has to act on a ball to change the momentum, right? Got that? So, if you look at this idea that change in momentum, well, change in momentum can equal a couple of things. And it can equal mass times change in velocity, okay? And that change in velocity can be written as V minus V naught, okay? Same thing we've written since the day you walked in this class, right? So that's mass times velocity, kilograms meters per second. Now, that can also equal momentum final minus momentum initial. Okay, so if you know the final momentum and the initial momentum, you can write it this way. Okay, all three of these are equivalent. Now, all three of these also equal force times time. Now, this is why you can express momentum as Newton seconds, because it's some amount of force acting over some period of time. So, when the ball was headed towards me, and I didn't exert a force on the ball, there was no force. Without any force, what becomes your change in momentum? If there's no force, your change in momentum goes to what? Don't make this difficult.
Zero.
Zero. And if there's no change in momentum, if this is zero, that means that there's no change in velocity.
Velocity or mass, because on here you say changing mass.
Okay? Now, here's what we're going to do. And Kendra, there's no way I'm going to have you do this.
Thank you.
Okay? There's no way I'm going to have you do this.
Okay.
Okay.
Is
But
that
we-
an egg? Is that an egg?
It's an egg.
And
Oh yeah, I'm not gonna do that.
Joking it.
Okay? It's a real egg.
Shake it, shake
Is
it.
there chicken in it?
Okay?
You can hear
Real
it.
egg.
Wait, so.
Okay, now, I'm going to throw this raw
Oh,
egg to you.
Grant.
Throw it.
I'm going to toss it. It isn't like I'm going to throw it.
Throw a cannon at it.
Okay? Now,
Let's
let's
see.
catch it and not break it. Okay? You ready?
You don't want to exert so much force.
Soft hands.
Okay. Now,
I was hoping you messed that up.
I'll
Oh.
exert a force on that one. Okay. Now, why did you instinctively catch the egg like this? What soft hand means in terms of this equation? When you catch it with soft hands, are you altering force, time, change in velocity, or the mass of the egg? What are you making? What are you doing with the force? You're making it what, bigger or smaller? Small.
Aren't you making the time bigger too?
Oh! So look, there's two ways.
Yes, that's what I needed today.
You needed that little confidence boost.
Something.
Okay? So here's the deal. When you go to catch an egg, you instinctively understand what's called the impulse theory of change in momentum. Impulse just means change in momentum. So there's two ways that Bugbee could have caught the egg. he could have just put his hand up and caught it like this. Okay? He could have. And the egg would come to a stop. Probably crack and run down his arm. But that's what he would do. So in that case, he would have a very small time. The force would be big. So when he cradles it, he has the exact same change in velocity. The egg comes in at a certain velocity and it comes to a stop. So by increasing the force, by increasing the time, that makes the force smaller and the egg doesn't break. Okay? Got that. Now, different way you can show this. So let's kind of turn around to the back here. No, you can stand up here, Mike. Okay. Okay. So, Josh. Joseph, over here. Hold that. Okay. And now hold the corners. So you're going to create like a basket. Okay. Now hold it up. Okay. Now at the top. That side up. That side up. Boom. There you go. Give me a target. Okay. So I'm going to take the egg and I'm going to throw it into the blanket. Okay? All right? Now, if this goes south, it's because you guys lose grip of the blanket. So don't lose grip of the blanket. Okay? And then also don't let the egg roll out the end. Okay? All right, so we're going to throw it kind of slowly. Right? So, all right? Okay? Now, in throwing it, did I change the momentum of the egg? Yes. Did the blanket change the momentum of the egg? Yes. Which one changed the momentum of the egg more? Me or the blanket? You. It's the same. Because I took the egg from like 0 to 10 meters per second. The blanket took it from 10 to 0. No. Hold on. Okay. Now I'm going to throw it a little faster. Okay. So hold that back up a little bit more. Okay. Ready? So throw it a little faster. Okay. Right? So good. Okay. So we're going to bring the heat on this one. Okay. All right. Ready? Okay. So
Let me see the two-seamer now.
No, that was it. That was my cover. All right. So here's the deal. We're good. Thank you, gentlemen. So here's the deal. So I take that egg and throw it as fast as I can into that blanket, and that egg doesn't break. But I take that same egg and I hold it just this high, and I drop it, and it cracks. Okay? So here's the question. So when you look at that equation, right? When I throw the egg, I'm starting it from 0 up to a certain velocity, right? Okay?
0 to 70.
Okay, 70, whatever. Okay? Now, the blanket's going to take it from 70 to 0. But the egg doesn't break because what does the blanket allow for? Time. Big time, small time. Longer amount of time, so there is a smaller amount of force. Now, what if I had missed the blanket and it hit the wall?
Small time.
Very, very small time, which would equate to a very big mess or force, right? And so the egg would go, right? Okay. Got the idea?
I think we should
got it? Good?
Yeah, I can't really get a visual representation.
Yeah, can we get
So, let's start with a velocity time graph. Okay? So when I go to throw the egg, oh yeah.
Are there any free body diagrams that go along with this lesson?
No.
Yes.
So I go to throw the egg, right? What's the initial velocity of the egg?
Pretty high. If we're not starting this.
How about 0?
Alright, so
Okay. So I'm going to take the egg from 0 up to, let's go with what you guys said, 70. Okay? All right? Back in the day, might have pushed 72. All right?
I honestly think that might have been around.
Okay. Now, at this point, it leaves my hand. It's going to fly through the air. what's this graph going to do?
Are you talking about the blanket?
No, no, no. This is me in the act of throwing.
And then it's gonna start.
At this point, it left my hand.
It's gonna start
Constant
slowing
loss.
down, but not a lot.
Okay, basically it's a projectile motion, right? So over that short a distance, we're just going to say that that velocity is going to be constant, right? Then it's going to hit the blanket, and then what's going to happen?
Go to 0.
Right? It's going to go to 0. So is the momentum changing in this area?
Yes.
Yes. Why?
The velocity.
Velocity is changing, right? So here I've got a change in momentum. Is my momentum changing here?
No.
No. My momentum is changing here, right? So, in which situation, the blanket or me, which one creates a greater change in momentum? They're the same. Okay? They're the same. Because I have the same change in velocity, same mass, everything is the same. Now, what would this look like if you were to draw a momentum time graph?
A lot, a little, a lot.
No.
Should they look the same?
Going to be the exact same. Why?
Because it's directly related to the velocity.
Yeah, what's the only thing that I have to, if I know my velocity, what's the only thing I have to do to get my momentum? Well, multiply it by mass. So my momentum time graph would look the exact same. Okay? The only difference is the fact that this is momentum because it's mass times velocity, but the shape's going to be the exact same. So here's the deal. So when you have a horizontal line on a velocity time graph or a horizontal line on a momentum time graph standpoint, your momentum is just constant. When it slopes, that's when you have a,
Change.
which is going to require a
Force.
force. Okay? Now,
Jedi Stoking.
Inclination.
all right, now, here's one graph to look at. And that's a force time graph standpoint. Now this one is going to be different. So, let's just look at the units. What's the force going to be measured in?
Newtons.
Newtons. Time's going to be measured in
Seconds.
seconds. So, let's look at what Bugbee did when he caught the egg.
Calgary, wait a second.
This dude off that.
Okay? So, what Bugbee did is that Bugbee exerted a force over a certain amount of time to change the momentum of the egg. Right? So, what Bugbee did is Bugbee exerted a certain small force over a certain amount of time. Right? Okay, I don't care what the numbers are. This is what the graphs look like. So, you had a small force exerted over a long period of time. So, what units is this area going to be in? I don't care about the numbers, just what units is it going to be in?
Newton seconds.
Newton seconds. Oh, because it's Newton times seconds.
Momentum. Sick.
So the area is in Newton seconds, right? So that area, because it's force times time, is going to represent the change in momentum. This isn't momentum, okay? It's change in momentum. Because if there's no force, there's no change in momentum. Okay, so on a force time, the area represents change in momentum, not momentum. Okay? Now, what do you mean?
How is there force when it's going through the air?
This is when he's catching it.
Oh, okay. How am I supposed to know this?
Because I said,
Okay.
this is when Bugbee's catching it.
But before that, he's not.
You got you on that one.
But the graph is
He
winning.
does have you on that one.
You gotta say you win.
And the dinosaurs walked the earth before I talked about this too. So, okay.
Yeah.
You got you on that one too.
Yeah, you're right. It's the T-Rex curve, my bad. Okay, so, now, what if Bugbee says, I'm going to be a rebel, and I'm going to catch it without having soft hands? Okay?
You should have done that.
What's going to happen to the time? It's
Small.
going to become smaller, right? But the egg is still going to come to a stop. So is the final momentum of the egg still 0? Yes. So, but now, If he has a short amount of time, then this graph is going to look like this.
What does that mean? Changing.
So what do you think is true of these two areas?
They're proportional.
They're the same. Because if you look at change in momentum equaling mass times v minus v naught, no matter how Bugby catches it, the final velocity is still going to be zero. It's still going to have the same change in momentum. So the only thing that we can do is alter the time. Now, anybody here ever do gymnastics? Okay, Kendra, this is in your wheelhouse.
Okay, this was a very long time
Okay,
ago.
I'm not going to make you do gymnastics.
Okay, I was just gonna say, I was like,
Yeah, I don't want you to do like a, flip up in the air, flip.
okay,
No.
okay,
Okay, but here's the question.
okay,
You're jumping off whatever apparatus.
yeah.
Okay?
Balance beam.
Balance beam. So do you want to land with your knees locked or with your knees bent?
Bent,
Why?
because that would really hurt if you just
In
leave it.
terms of this graph,
If you did it straight,
You get more points.
Because
this
that,
is Kendra, not you. This is not Kendra.
maybe you're gonna
because that would be a lot of force
knees
on
outside of your skin.
your body.
Okay, but in terms of this graph, if you land with your knees locked, what does that do to the time?
It takes it down, it goes shorter,
So that makes the force
greater,
greater. Now, when you land like this, it makes the time
longer,
and the force becomes
shorter.
shorter. Okay? If you are a safety engineer for Ford, Chrysler, whoever, you live and die by this equation. That force times time equals change in momentum. What's the whole role of airbags, seat belts, anything in that car? The padding, what does it do? It makes the time big, so the force becomes smaller.
Small.
Okay? Every safety engineer, this is your equation.
Big,
right
small.
here.
So that's like the only.
Huh?
Wow, I should have done that. That seems pretty.
Yeah, pretty easy. Just walk in every day.
I know the momentum equation.
Change the momentum. Oh, now,
Hey, I have a question. Okay, so theoretically, if you knew the speed off a bat and the angle at which it's hit, you can calculate where it's going to land, right?
Yes.
Okay, cool. Thanks.
that was it.
Yep.
Okay.
Right before it.
Everybody knows
If you
that.
know the position of the moon, I can tell you where it's going to be in 1,000 years, and I can
Yeah,
tell
I'm
you
just
where it
saying,
was with the
like,
dinosaurs.
just because you just told me that, I'm going to give you part of my profits for one of my angles.
Okay, all right.
Thanks.
Can we negotiate a percentage?
No, you're not.
5?
You're not there yet.
Five?
You're not there yet.
1?
Well, what's your
All right,
How
investment?
about a shout out?
You're kind of convincing me not to even like do it anymore.
Are you gonna make an
Oh, come
investment?
on.
You're being really clingy now. And
I mean, this is
not-
190.
I'm not being clingy.
That's what they all say.
That is what they all say.
Okay,
I'm not being clingy.
so let's say that we've got a carrot car
Oh, carrot cars.
with mass of 10 kilograms, and it's moving at, I don't know, 20 meters per second. Dude, come to a stop. Okay? All right, stop.
Momentum is 200 newtons.
So, Mr. Rollins, does the momentum of the car change?
Yeah.
Yes. Why?
Velocity change.
Velocity changes. Yeah. Do you have enough information to calculate the change in momentum of the car?
Yeah.
Yeah. Because you know, change in momentum equals,
Mass times v minus v naught.
okay? Now, this is what you're going to do wrong. What's the change in momentum, Mr. Rollins?
Newton seconds.
What's the numeric, what's the units? I want the actual number.
Oh, you need your number?
Yeah.
Zero.
I gotta think. Is that 2,000?
Neither.
No, it's neither. Hold on. I gotta think.
No, Kyle.
What's the change in momentum?
2,000 hassle.
You take a pass. Yeah. Would you like to phone a friend?
Calculation.
Okay, you're going to phone your calculator friend.
That's
200.
Wait, what? That's what we were trying to find.
You got
Change
it
in momentum
wrong.
is 200 newton
Wrong.
seconds.
No, that's
Wrong.
wrong.
Bad, bad, bad.
I realized it after I said that answer though.
Okay, now,
Why is that bad?
don't even,
Can't even look at you anymore.
don't even.
Why?
Okay, look, Captain Triton,
Negative.
okay?
Oh, he got you. Minus 12.
They are.
Okay,
Yeah, you thought you were
Dude,
getting.
I'm
Let's
sure
say
you're
you're going so fast.
I'm gonna show you what I
that
I did the exact right thing. I used the wrong number.
so here's what you have to pay attention to, is that it's V minus V naught. So it's 0 minus 20 times 10, that has to be a negative 200 newton seconds. Now, do you have enough information at this point to calculate the force?
no,
No, why?
you don't have the time.
You don't have the time, okay? Don't have the time. So, let's say that you're driving along, right? And you know that the light's gonna be red and you coast to a stop, right? And let's say that this time was 10 seconds. If you know the time is 10 seconds, now can you find the force? Mr. Bugby? Why? Yeah. So, if force times time equals change in momentum, which in this case is going to be negative 200 newton seconds. So, if I take that, to get that force, I divide by this time of 10 seconds. Miracle if miracle happens, the seconds cancel out, you're left with, and that's what force is measured in. Right? So in this case, 200 divided by 10, Mr. Rollins, is what? 20. Positive or negative?
Negative. Because it's negative 200 divided by positive
So it's going to be,
10. Negative.
force is going to be negative 20 newtons, right?
Over that 10-second period.
So here's where this goes south. If you had done a change in momentum that was positive, then you would get a positive force. So you're going to tell me that you're going to take a car that's moving with a positive velocity, you're going to bring it to a stop by applying a positive force to it in the same direction that it's moving. Bad. Okay? Not going to happen. Okay. So that's situation number one. Situation number two. Same car. Okay? Mass is still 10 kilograms. It's still moving at 20 meters per second. Whoop! We're still going to make it come to a stop. Okay? But now the time is going to be 5 seconds. Okay? Now, Sam, Mr. KU, what's that going to do to my change in momentum?
Wait, the time being half?
The time went from 10 seconds to 5 seconds. We're still at 20. We're still coming to a stop. Mass is still 10 kilograms. So what's that going to do to my change in momentum?
Increase it?
Why?
Because you do.
Wait for
Come
it.
on, Mr. Real
I
Chris.
do it now.
Mr. Gilchrist. You can do it.
You're talking about changing momentum.
I am talking about changing momentum.
Wait, it would be the same, wouldn't it?
Oh, it would be the same. Beautiful. Okay? That's why I said wait
Like he
for
really
it,
drew
right?
like arrows there, but I was like, oh my god.
So I still have 10 kilograms times 0 minus 20. 0 minus 20. So I'm still going to have the exact same change in momentum of negative 200 newton seconds. But what's going to happen to my force?
Go
Up, because I'm going to stop in a
Shorter
amount of time. Okay? So here's the deal. So if you look at this force time situation, situation number one, I had a negative, it would actually be here's, I will make it right. So here's 0. So situation number one we had a negative 20 Newton force acting for 10 seconds. Situation number 2, I would have, if I took negative 200 and dividing it by 5, I'd get what?
40.
What's 20 divided by 40?
4.
Or
4.
I could have negative 40 acting over 5 seconds. So no matter what, what's going to happen to the area? It's going to stay the same.
Hashtag same.
Okay. Now, here's the deal. From a momentum standpoint, what's the role of the gas pedal in your car?
To increase the moment.
Yeah. Okay? Your gas pedal makes the momentum vectors bigger. The brake makes the momentum vectors smaller. And your steering wheel changes the direction of it. Okay? All right? Your steering wheel changes the direction of it.
Spinner vector.
It does.
Changes the direction of the momentum
You
vector.
got me dead, brother.
Now, there's a couple of ways that you can look at this and additional. So we just said that force times time equals change in momentum, which is mass times V minus V naught. So what if I divided both sides by time? Okay? What's going to happen over here? What do I have left? Force. Okay. So I get force equals mass times V minus V naught over time. Well, what's V minus V naught over time? Acceleration. So basically all this is remanufactured F equals MA.
What?
It is.
My mind is blown.
Everybody just lost 3
Meters?
What?
Meters?
Oh, it's math. Meters. I kept thinking that was meters. I was like, meters, cute. Seconds. Everyone, make sure you're gonna do this wrong. You're gonna think the M is meters. It's not.
That was the speech I gave the second day of this
You're
class.
gonna do that wrong. He just proved you will.
You just proved we will.
Slack.
Okay.
I did that yesterday.
Now, think this through. I want to create a big change in momentum. Okay? So what we focused on so far has been keeping change in momentum constant. Now I want to change the value of change in momentum. So I want to create a big change in momentum. So here are my options. I could have a small force acting over a long period of time. I could have a large force acting over a short period of time. Or I could have a large force acting over a long period of time. What will create the greatest change in momentum of those 3 combinations?
I didn't think time was it.
Huh? So, small force, large time. Okay?
Nope.
Large force, small time.
Yep.
Large force, large time.
Large time.
Ms. Treadway, what'd you say?
But large force, large time.
You are correct. Why?
Well, I mean, if you like look at the graph, it'll be a bigger area.
Yeah, if you look at the graph, right? If a force time graph, the biggest force acting over the longest period of time will create the greatest area, which is going to be the greatest change in momentum. So, if you look at this, like let's say you want to hit a softball. You want to go yard, right? Or the Cubbies want to hit a home run.
Cubby again tonight.
So here's the deal. Look at the situation between laying down a bunt versus hitting a home run.
Oh.
Okay?
You never bunt.
Sometimes you need to.
Kent Murphy rule
So
number 1,
here's the
never
deal.
bunt.
If you want to bunt, what do you want to do? You want to change the momentum of the ball very much. If you want to lay down a good bunt, you want the momentum of the ball to change very much. No, the ball's going to be coming in. You're going to hit it with a soft bat, right? So that it dribbles away, right? That's the whole idea of the bunt. You don't want to change the momentum of the ball very much. So you exert a small force over a short amount of time. Now, if bases are loaded and you're down by 3 runs, you're up to bat, you want to hit a home run. You want to exert a large force on that ball over a certain amount of time to create a big change in momentum to make the ball travel a great distance. Okay? Makes sense. Good.
Who wins tonight?
I think the Cubbies do.
Cubby,
I don't know, but I think
If the Cubbies win
the
this World Series, we don't have any more tests.
No, listen, so if,
Okay, look, I'm already throwing you a bone.
All right.
Okay?
Cubby.
All right, so stop that. So let me go over a couple of things about this. When you look at this assignment, when you see the word impulse just means change in momentum. Okay? So when you see impulse, that's just change in momentum. Now, when you get to question number 8, okay? Hockey player exerts a force of 40 newtons on a hockey puck for 0.1 seconds. Sketch a force time graph. Okay? It doesn't have to be done on graph paper, but you do need it to be done big enough where I can see where this thing is. Now, you're actually going to end up adding to that when you get to number 10. So, you're going to use this force time graph both on number 8 and on number 10. So, you're going to need to add on to it when you get to number 10. It'll make sense when you get there. So, leave enough room so you can add on to this force time graph. Okay, just don't stop it and go, oh, here it is. Okay, anyway, you're on your own.
I like
So-
this. This is cool.